Okay, good morning. Last lecture we stopped at this problem. I guess in the previous posted video lecture I talked about it, and I included one more slide with the solution for this problem. Again, we will go through it very quickly here. We have a straight line of a mass 15 gram that is 2 meter long, carries a current of 8 ampere. This wire is aligned horizontally with the current going from the west to the east. You want to support the wire against gravity using the weakest possible uniform external magnetic field. Which way should the magnetic field point? So if we go to the solution that I have added, here we have the wire laid out horizontally with the current I going from the west to the east. Then the gravitational force would be, as you can see here, Fg pointing downward. So we need at least an opposing force that at least equals this gravitational force. We said that this force would be the magnetic force induced due to the existence of this current with the magnetic field that we need to apply a uniform magnetic field. We need to find out the direction of this magnetic field. So as we've seen earlier, using the right hand rule with the fingers or with all the fingers and the thumb, you can see that if you point this finger toward the current and this finger toward the magnetic field, the thumb would be pointing toward the force. So you always look at it as A cross B, for example, going to give you A cross B. So this is the resulting vector. If the current is A, the magnetic field is B, then this force here or this vector here would be A cross B. So the thumb will be pointing toward the force. So let's look here using the right hand rule. If I have the current going in this direction, I have the force pointing up to oppose the gravitational force, then this finger should be pointing toward the magnetic field, which is entering the screen. That's why we had the magnetic field here, as you can see, pointing into the screen. So that's the direction of the magnetic field. Then we need to calculate the value for this magnetic field. So we said the gravitational force Fg equals to mg. G is the gravity, is the acceleration, and m is the mass. And we also have the magnetic force given as I L vector cross B vector. Okay. Then the magnitude would be I L B sine theta. So let me take so here this is the magnetic force that equals to I L vector cross B, and we know that the L vector cross B vector equals to the magnitude of L times the magnitude of B times sine theta in between. So here, in order for those two forces to be equal, take the magnitude of both and equate them. So I have mg equals to I LB sine theta. Now, since theta is a 90 degrees, the angle between the current and the magnetic field, as you can see here, the magnetic field is into the page. The current is horizontally from left to the right. Then the angle between the current and the magnetic field is 90 degrees. That's why sine theta would be equals to 1. So in this case, I have mg equals to ILB, and then if I rework the equation, B equals to mg over IL. M is 15 to the power minus 3 in kilograms. G is 9.8, and the current is 8 ampere, and the length is 2 meters, and then the answer would be the magnetic field. Was that clear? Okay. So let's move on now to this loop. That's a rectangular loop with the width of L and a height of W, with the current, as you can see, going counterclockwise, and the magnetic field is pointing upward. So if we want to calculate the magnetic force on each side, I want to calculate the net force in this case, then by understanding that the current here is parallel or anti-parallel the magnetic field. So we have here, as I said, two sides that are parallel to the magnetic field, which means that the theta would be 0. And that's why at this position, the force on this side is 0, and the force on that side is 0. So we're only left with two sides, the top and the bottom one. If we look at the top one, we have the current going in this direction. If we use the three fingers in the right hand, we have the current going in this direction. We have the magnetic field pointing up. So in this case, if we have the current going in this direction and we have the magnetic field pointing up, then the force would be pointing toward the screen. So in this case, if I look at the force on that side, it would be pointing toward the screen. I can represent it by this. So that's the force on the side. If I am to evaluate now the bottom one is the opposite. I have the current going in this direction. I have the magnetic field pointing up. I have the magnetic field pointing up. I have the current going in this direction. And then the thumb would be pointing out of the screen. That's why I can represent the force, the magnetic force on this side by this. So I have the first force on the side pointing toward the screen, the bottom one on that side pointing out of the screen. So the net force in this case, if you look at those two forces that are in opposite directions, however, they are equal, the net force on that loop would be 0. The net force on that loop would be 0. However, although it is 0, they are applied, one of them at the upper side, the top side, and the bottom side. This is going to result into a torque. Although the net force is 0, but here the torque is not 0, and this will cause this loop to be rotating. So if this is the loop, I have the first force pointing into the page, the second force pointing out of the page. This is going to result into that loop rotating this way. Okay. Now, this is the loop that we were discussing, and we said that the top side has the force pointing into the screen, the bottom one out of the screen, and this is going to cause this loop now due to that torque to rotate around this dotted line axis. So if I am to look from this side, imagine that you are now standing from the side and looking at the loop. This is what you're going to see. What you are going to see is this side here, and this is the force, the top one. When we were looking at the screen here, and this on that from that side, we saw that the top force is pointing into the page, the bottom force is pointing out of the page. This is the one that is pointing into the page. So this is, I call this one F1, then this one is F1. If I call this one F2, then this one is F2. Although they are equal, those two forces are equal, and that's why this loop now is going to rotate this way. This loop is going to rotate this way due to that torque. Now, how do we calculate this torque? We know that the torque equals to F times the length here, which is W over 2. I have torque 1 and torque 2. So the total torque is the torque 1 plus the torque 2, which is the torque 1 here is the force times the length, which is the W over 2. The whole height here is W, as you can see. So we have here the torque as for torque 1 as F times W over 2 plus F times W over 2 as well. This is going to result into F times W. So the torque equals the total torque is F times the total length between those two forces, W. Now we will introduce the magnetic dipole moment, mu, as we will see later on in the next slide. And where the torque is mathematically represented by this mu cross B. Okay, so we said the mu is the magnetic dipole moment, and this magnetic dipole moment that we have seen earlier, the torque equals the mu cross B. This magnetic dipole moment is given by the current times the area of the loop times the normal unit vector on that loop. So how do we define this? So this is again for a loop that has only one loop. If I have several loops of wires making a coil, in this case I have to include the number of those loops, because this means more current going into that loop. So if I have a current going from only one loop and I have another, another coil that is made of several loops, the equivalency for the second one basically is multiplying this IA with the number of the loop, which is the number of the loops in that coil. So the more loops I have in the coil, the stronger magnetic dipole moment I have. So the magnetic dipole moment in general is represented as N, the number of the loops in that coil, times the current times the area of that loop. And the direction would be pointing normal to the area of that loop, such that if we follow the right hand rule, we want to know the direction of this normal unit vector. You take your fingers that are curling, defining the direction that those current is going through. So in this case, if I'm looking at the screen right now, I see that the current is going counterclockwise. If the current is going counterclockwise, then the thumb here defines the direction of the magnetic field generated or the magnetic dipole moment for that loop. So I have here going counterclockwise, so which means going this way. Then I have the normal unit vector pointing up. We will see this one in the coming slides. So this is what I was referring to. If you look at this one single loop, and the current is going counterclockwise, you will see that this is going to result into generating a magnetic field into that loop. This magnetic field generated due to the current going and counterclockwise. Again, the direction of the current is defined by the fingers, how they're rotating, and then the thumb is the generated magnetic field or the magnetic dipole moment. For both of them have the same direction, magnetic dipole moment and the magnetic field. So the magnetic dipole moment would be pointing, as you can see here, upward. This is equivalent to uh, a magnetic bar. If we look at the magnetic dipole moment for the magnetic bar, will be pointing from the inside, from the south toward the north, where, if you recall, we have the magnetic field uh, in the magnet, in the permanent magnet, always going from the north toward the south. So if I am here to draw the magnetic field lines, there will be doing something like this. Pointing from the north toward the south, where the magnetic dipole moment is going inside from the south to the north. So that's the magnetic dipole moment based on the right-hand rule. Again, take your fingers at the direction of the current, curling in this direction. Then you have the magnetic dipole moment pointing up, perpendicular on that loop. So as examples, I have one comment here. Yes, as we'll see later on, it's always aligned with the magnetic field. And whenever you have a loop and an external magnetic field, as we will see later on, that loop that is generating a magnetic field will always have its magnetic dipole moment aligning with the magnetic field, as we will see later on. So those are, as I said, examples of the magnetic dipole moment for a magnetic bar. And the magnetic moment of the Earth is, as you can see, in the range of 10 to the power 22. The unit is meter squared ampere. So those are some of the examples of the magnetic dipole moment. Now let's go to this question, where basically explains what we were just saying, that if I have a loop, one single loop, here what we are only seeing is the cross section of this loop. What we are seeing here is the cross section, only the cross section of the loop. There is a full loop. What we are looking at is the cross section, as if we have cut it from the middle. That's why we're seeing the two cross sections. Here in this loop, we can see that the current is entering here, leaving there, which means the current is going this way. That's why the magnetic dipole moment is pointing in this direction. The second case B, we have the current entering here as well, leaving here. So we have the loop tilted. That's why if we follow the right-hand rule, then you will see that the magnetic dipole moment is pointing tilted, where the other one. So here the magnetic dipole moment is pointing this way. Here the magnetic dipole moment. Can you please mute your microphone? Thank you. The magnetic dipole moment is pointing this way, and here the magnetic dipole moment is pointing this way. The question is asking, rank the magnitudes of the torques acting on the loop from highest to lowest. All loops are identical and carry the same current. Based on the loop, on the torque applied on that loop. Why? Because as we have seen, this generated forces on that loop will result into a torque, and this torque will basically twist or rotate the loop such that the magnetic dipole moment is always aligning with the magnetic field. So this is the external magnetic field. That's the external magnetic field. The torque applied on that loop will always tend to rotate it such that the magnetic dipole moment is aligning with the magnetic field. So this is the external magnetic field. In this way, the magnetic dipole moment will cause, or the torque induced on that loop will cause it to align. So in this case, where I have the torque given mathematically by mu cross B, in this case, the angle between the mu and the B is 0. And that's why this case is the case that has a torque of 0. Now, if we look at the second case, there is an angle between the magnetic field and the magnetic dipole moment, and that's why here I have torque defined by mu b sine theta. If I look at if this one is theta, so here I do have a torque. This torque will tend to force that loop to completely rotate and align as the case A. However, if I look at now the torque applied on this loop that is laid down horizontally, it should be greater than this one. Why? Because now the angle here between the magnetic field and the magnetic dipole moment is 90 degrees, which is going to result with the maximum torque applied on that loop. That torque is trying to rotate it to make it such that the magnetic dipole moment is aligned with the magnetic field. So if we want to rank it, we saw that the torque in the C case is the highest, then comes B, then comes A. So the answer would be B. C is the greatest torque, comes the B, and then the A. So we said that the torque equals to the magnetic dipole moment. No, no, no. The green arrows here are the external magnetic field. The current is entering. The current is entering this point, leaving that point, and what you are looking at is the cross section of the loop. You have a loop that is sitting this way. Let's assume that this loop is sitting that way, and then when I say you're looking at the cross section, it's like cutting the loop this way, and you're looking from here. So what you're seeing, the current is entering from here, leaving from there. Think of it as a complete loop. So in this case, if the current is entering from here, leaving from there, then the current is rotating this way, and you have if the current is entering from here, leaving from here, then you have the current going this way. That's why the magnetic dipole moment is looking or pointing in this direction. Yes, the perpendicular one has the highest torque. Yes, that's the strongest. That's correct. In this case, in this case, we also define the potential energy due to the orientation of that loop in the existence of the magnetic field, certain magnetic field, and here we need to distinguish between two cases. In case the magnetic dipole moment is parallel with the magnetic field, and we saw in that case the torque would be zero, and we are going to call that position as the lowest potential energy position. Why? Because there are no torque, there are zero torque applied on that loop. Also, the second case where the torque is also zero, if I have the magnetic dipole moment aligned anti-parallel, although the torque is zero, but think about it. If the loop is allowed to is free to move, then this loop will flip all the way till it comes to the position where the magnetic dipole moment is aligning with the magnetic field. So if the magnetic dipole moment is parallel with the magnetic field, this is the position with the lowest potential energy. If I flip this loop and make the magnetic dipole moment anti-parallel, if the magnetic field is pointing in this direction, we said if the magnetic dipole moment is pointing in the same direction, aligning with the magnetic field, the torque is zero, yes, and this is the lowest potential energy position. Now, if I rotate this magnetic dipole moment, I rotate the loop such that the magnetic dipole moment is anti-parallel. This is the location where I have the maximum potential energy. And as I said, if the loop is allowed to move, this position will be, although the torque is zero, but it is an unstable, will result into the magnetic dipole moment flipping back and aligning to go and align with the magnetic field. In both locations, if the magnetic dipole moment is parallel or anti-parallel, the torque will be zero. Why? Because the theta between the magnetic field and the magnetic dipole moment will be zero, which means the torque is zero. Because we have said that mathematically tau equals the torque equals to mu vector cross b vector. So the magnitude will be the magnitude of the mu times the magnitude of b times sine theta. If theta is zero, the torque is zero. So those are the two special cases when the magnetic dipole moment is parallel or anti-parallel. The torque is zero. However, one of them, when it's parallel, is considered the lowest potential energy, and when it is anti-parallel, is considered the maximum potential energy. And that's why the potential energy here is given to me as U equals to minus mu vector dot b vector. It is the dot product between the magnetic dipole moment minus magnetic dipole moment dot the magnetic field. Okay, now let's move on to this question. We have here a loop, one single a loop actually is made of n turns. So we have a loop that is made of N turns with an area of A and a current of I. This coil, we call it a coil that is made of several turns, is free to rotate around along the x-axis. So it's free to rotate around along the x-axis. We have the current going, as you see here, counterclockwise in this loop. We have the magnetic field pointing upward. So we have the loop sitting in the XY plane. So this is the XY plane. This is the coil sitting in the XY plane. It has a current going counterclockwise and allowed to rotate along the x-axis. It has a magnetic field pointing upward, uniform, in the y direction. What is the magnetic dipole moment for this coil? Very simple. You just look at how is the current is moving, and you curl in the direction of the current. Then the thumb here will give you the direction of the magnetic field or the magnetic dipole moment. In this case, I have the current going this way. Now, probably the video here, if you look at it, and just want trying to make sure that you understand the direction here. The camera is taking is capturing a picture that I'm rotating this way. This is exactly how it's looking to how I can see it on the screen. It's going rotating in this direction. Then the thumb is pointing out of the screen. In this case, the magnetic dipole moment will be going in the direction of the positive z, the positive z. So the answer would be B, magnetic dipole moment based on the direction of the current is pointing out of the screen. And out of the screen, if I look at my coordinates here, out of the screen would be the positive z axis. The second question is same coil that is in the XY plane, same area A, number of the turns is N, and the current is I. Again, the coil is free to move. The coil is free to rotate along the x-axis. Along the x-axis. The field is in the y. What do we need here to calculate or to find? What is the torque exerted on the coil? Okay, so this is a counterclockwise. That's a counterclockwise, and the magnetic dipole moment is pointing out of the page as we have seen before. Yeah, okay. So if the magnetic dipole moment is the direction of the B field effect, of course, because at the end, remember, when you calculate the torque mathematically, it is the magnetic dipole moment cross the magnetic field, which is the magnitude of the magnetic dipole moment the magnitude of the magnetic dipole moment times the magnetic field times sine theta. So what is theta? Theta is the angle between the magnetic dipole moment and the magnetic field. So yes, it does matter. In this case, the case that we have right now, I have the magnetic dipole moment on the same direction of the z as we said here. So the angle between the magnetic dipole moment right now and the magnetic field is 90 degrees. So this coil will rotate. This coil will rotate such that the magnetic dipole moment needs to align with the magnetic field, so it will rotate this way. It will rotate this way such that the magnetic dipole moment is aligning with the magnetic field. So yes, the direction of the magnetic field does matter. Okay. So this loop will rotate along the x-axis, as we can see here, and the torque, exerted torque, will be NIAB, where this mu is NIA, and the V here and the theta here is 90 degrees. That's why this one is 1. We'll end up with NIAB. Yes, so that's correct, Julia. We have here we have here a second way to look at the magnetic field generated from a current. A magnetic field generated from a current, a DC current flowing into a loop. The fingers in this case will be the direction of the magnet of the current, and the thumb will point toward in the loop, and the thumb will point toward the magnetic dipole moment or magnetic field direction inside that loop. I am looking at the magnetic field generated by the flow of the current. So when I have a current flowing into a loop, this current flowing into a loop will generate a magnetic field. The direction of the magnetic field is defined by the right-hand rule, taking the fingers as the direction of the current, and the thumb as the direction of the generated induced magnetic field. So that little loop is going to generate a dipole, it's acting like a dipole. This dipole has a magnetic and effective has a generated magnetic field such that the direction inside this loop is pointing based on the flow of the current. So if the current is flowing in this loop counterclockwise, the thumb will point toward the magnetic field generated due to this current in this loop. Okay, okay, that's good. I'm answering, by the way, uh, some of the questions by your colleagues on the chat. As I said, if you look at the current is flowing here counterclockwise in this loop. So if you take your fingers as the direction of the current, then the thumb would be the direction of the induced magnetic dipole moment or the induced magnetic field inside this loop. So this way, the thumb is the direction of the magnetic field generated by that current going into this loop. Okay, now let's look at the third question. Again, the torque will always try to align, push, or rotate that loop, trying to align the magnetic dipole moment generated with the external magnetic field. So it will always, so if I have this loop sitting this way, then the current is going in this direction, then the magnetic dipole moment for that loop is pointing up, right? Pointing up. If I have the magnetic field pointing in this direction, the torque will always tend to rotate this magnetic dipole moment such that the magnetic dipole moment is aligning with the magnetic field. Now, if I have the coil and the magnetic dipole moment is aligning this way, and I have the magnetic field is in this direction, right? Although the torque here is zero, but as I said, this position is an unstable position. Any small motion will result into that coil flipping and coming in this way, such that the magnetic dipole moment is aligning with the magnetic field. That's why we said in this location, if I have the coil sitting in this location with the magnetic dipole moment anti-parallel with the magnetic field, this position is considered the highest potential energy, and that's why it tends to flip and rotate such that it loses energy and it goes to its lowest potential energy position. Okay, in 2 minutes we will finish the lecture. The thumb is the magnetic dipole moment. That's correct. Because this torque is going to rotate that loop such that the magnetic dipole moment is going from Z aligning with the magnetic field, which is along the Y axis. Okay. Now let's move to the last. Let's move to the last slide before we stop. Again, we have the same coil, same area A, number of the turns N, and the current I. The coil is free to rotate along the x-axis. The field B is in the y direction. What is the torque exerted on the coil? So now we have the y pointing into the page. We have the loop in the XZ plane, and we have the magnetic field pointing in the y direction. What is the torque exerted on the coil? Remember, the torque equals to what? The torque mathematically is mu b sine theta, right? And we know that mu is NIA. How much is theta in this case? So if we look at this loop, and we see that this loop if we look at this loop, we see that this loop is having the current going clockwise, right? I have the current going clockwise. This means the magnetic dipole moment will be pointing along the y-axis. If I have the magnetic dipole moment pointing along the y-axis, and I have the magnetic field also pointing in the y direction, then the magnetic dipole moment is parallel with the magnetic field, which means that theta is 0, which means that sine theta is 0, and the answer would be 0. The torque here in this case would be 0. Yeah, yes, that's correct. And I think our time is over. We will stop here and we'll see you on Friday. Okay, any question before you leave? Thank you so much. Yeah. One more time. Y, it is C and the last one. No, because the magnetic dipole moment is already parallel with the magnetic field. So the angle theta is 0. And that's why the torque would be 0. Okay, the next, I think you mean this one, right? Yeah. In this case, the magnetic dipole moment, the magnetic dipole moment, due to the rotation of the current, this way, to me it looks counterclockwise. The magnetic dipole moment will be in the direction of the z, and I have the magnetic field in the direction of positive y. Then the torque will rotate this loop along the x-axis such that the magnetic dipole moment is aligning with the magnetic field. So the rotation is happening here around the x-axis, which is C. It is rotating along the x-axis. So it's doing like this, such that the magnetic dipole moment is aligning with the magnetic field. So yes, it is C. Well, the torque here is represented by the B cross the mu cross B mathematically. You look at it as only mathematically. The rotation is happening such that this magnetic dipole moment is aligning with the magnetic field. The torque is induced such that the magnetic dipole moment will align. The magnetic dipole moment is going to be aligned with the magnetic field, going to become parallel with the magnetic field. So the magnetic field is pointing in the positive Y. The magnetic dipole moment is pointing in the positive Z. The magnetic dipole moment is going to rotate such that it will become parallel. So if the magnetic field is pointing up this way, and the magnetic dipole moment is pointing in this direction, which is the Z, it will rotate such that it is aligning, becoming parallel with the magnetic field. Yes, very soon. I'm finalizing the grade. I'm working on putting all the grades together. Okay. Now we can, for you who wants to attend the office hours, we can switch to the office hours room. I have it posted there. The ID is there. We can go there now for you who wants to have questions and ask questions in the office hours. We're going right after the end of the session. So I'll see you there. Okay? Thank you. Thank you. I'll see you in the office hours session.